Okay, so last lecture we were just finishing off this question. So let's just go back and finish this one off. The situation that we had was we have like two skaters here. They're holding a pole. One has twice the mass of the other person. And so this pole, and the first question was, where do the skaters meet if Fred pulls hand over hand towards the pole so as to draw himself to Ethel? And I think previously we already worked out the position of the center of mass. So what do you think the answer of part A would be? This is Fred, by the way. You understand the question? So only Fred is pulling, and then the other one is just holding on. No guesses? If you were to guess, which one? Yeah. Correct answer is A. So I think the way to think about this whole problem is that, so we've been doing center of mass, right? So we have this system here, and because they're on ice skates, we can basically consider this a sort of an isolated system in terms of the motion in the x direction. So if you consider this whole thing, then initially there is the center of mass is just at this position here, L over 3, the distance from Fred, right? So now because there's no forces that act externally on this system, so if you remember we were doing something like if we have a combined system, right? Then we can also apply F equals ma to the combined system, yeah. But the thing is that we have to we don't have to count the internal forces between the systems. So this Fred pulling the stick is basically an internal force of this whole system, right? Because that's within, and basically nobody's pushing these guys from the outside. So basically the total force on this combined system is 0, and they're stationary, and what this basically F equals ma will tell you is that the acceleration is 0. And if the acceleration is 0, and if they're stationary, then whatever happens, basically the center of mass is not going to change, right? So when when Fred pulls along this pole here, basically what's going to obviously end up is that, you know, these guys are going to be like kind of stuck together, right? So eventually it's going to be like this, and well, I guess the pole will be sticking out like this. But the pole doesn't really matter, it's just a way to transfer the forces. And basically these guys will be together and they're on the same position. So basically their center of mass is wherever they are, just, you know, they're stuck together. So we know the center of mass is here at L/3, and because the total force, the total external forces is 0, we know that the final center of mass must also be there too. And so basically the only way for this to happen is if this is at L/3. So basically they end up where the center of mass is. Okay, so now that we've broken it down like that, the rest should be easy. So what if Ethel pulls herself towards Fred? So what would it be in that case? That's the smaller mass, smaller person.
Still A.
Yeah, still A. So the only thing that's different now is that, you know, she's pulling herself, but you know, they still end up the same position. She's pulling it, so this time the poles are going to be sticking out like this. That doesn't really matter because the pole doesn't weigh anything. So yeah, still L/3. And if both skaters pull hand over hand, then I think you can now see that it doesn't matter. They still end up at L/3 from Fred, so part A. Okay, but yeah, if you didn't really know this kind of idea, then, you know, it looks a little bit complicated, right? Because, I mean, you know, there's some force that pulling on it, you don't even know what the force is, but then by using the center of mass concept, you can actually easily work out where it is. Okay, so then we move, oh yeah.
Wait, so the explanation is that since A is 0, because there are no external force, only internal forces.
Yes.
That's why the center of mass never change.
Yeah.
System.
Yeah. Yes. So I think you can basically deduce that they're not moving at the beginning. Two skaters are, okay, well, it doesn't really actually say it exactly, but I think it's sort of implied that basically the center of mass initially is at L/3. The velocity of the center of mass is 0 because they're not moving before, and because the total force is 0. Sorry. This implies that the acceleration of the center of mass is also 0. And well, if the acceleration is 0 and the velocity is 0, then this has to stay in the same position. That's the logic. Yeah, it might be clearer if they said that they are both stationary. I mean, I think the question should really say that just to make sure that that's not ambiguous. It's a little bit, you know, it's kind of implied in the question, but it's not exactly stated. So, yeah. Okay, so now let's just go on to the final topic of this chapter, which is momentum. So probably some of you might have seen this before too, but we can also define a thing called momentum, which is defined just in this way. This is really just a kind of a definition, but we'll see why it's a definition that is useful. And so the momentum is defined as the mass times the velocity. And so we can, if we make that definition, then we can kind of relate it to the force, because we know that if P equals mv, we know that F equals ma, and well, we know that the velocity and acceleration are just related by a time derivative. So if you calculate what the derivative of the momentum is, time derivative of the momentum is, then we say that mass is not going to change, right, with time. Then basically we've got mv, which is ma, which is the force. So from that definition, we can already deduce that the change in the momentum is actually equal to should be equal to the force, right? So the way that we might picture that is something like this. We got something, so momentum is a vector quantity because you multiply it by the velocity, and the velocity is a vector quantity. And so here's the momentum at the beginning, and let's say some force acts on it, it'll change the direction of the object, and so the momentum will be also pointing in a different direction. And we can say that the change in that momentum is related to the force. So the force acted on this to change the velocity or the momentum, and so it this difference in the vectors basically is this P final minus P initial is equal to this force multiplied by whatever time interval, how long that took to do that change, right? So that's another way of basically viewing this, and then this is the derivative form of that, which you can do by basically taking the limit of this thing for very small times. So the force should be equal to the change in the momentum divided by the time interval, and that's basically what this is saying here. So time rate change of momentum of a particle is equal to the net force acting on the particle, and it's in direction of that force. So yeah, so if you basically if you look at how much the momentum changes, if you do the difference in the initial and final momenta, that's basically equal to that's the direction of the force that's acting on it. So some force in this direction is the reason why the momentum of this change from going like that way to that way. Okay, so what if you have more than one particle? Well, we can add up the momentum of the whole system just by simply adding up the momenta of each of the subsystems. So if we've got like 3 particles here, this one's got momentum this way, this one's got momentum that way, and this has got momentum this way, then the total momentum is just simply the vector sum of these 3 momenta. And so we can define the total momentum like this. So obviously it's equal to that. And just like we did when we related it to the force here, we can relate the total force, we can relate the total momentum equal to the total force on the system like this. And just to see how it works. So let's just, if we calculate what this is, so we just define the total momentum as momentum of each one, right? Dot dot. And because the sum, derivative of the sum is equal to the sum of the derivative, we can do this. And from the previous slide, we already know that each one of these is actually equal to the force acting on the particle. So this is basically equal to the total force. And here we more or less just define this thing actually. But we can actually relate it to another quantity, which is the velocity of the center of mass, right? So here's a formula for the center of mass for multiple objects. And we can also talk about the velocity of that center of mass, right? So in this case, maybe for these three things, if they're the same weight, they're somewhere in the middle here. That's the position of the center of mass. Now, if this whole thing is like moving somewhere, then obviously the center of mass will also be moving somewhere together. And we can write the velocity of the center of mass in this way, just by taking the time derivative of this. Again, all the masses don't change in time. So the only things that change in time are the positions. And so that's why only the positions become different here. And if you look here, at the top here, well, that's actually exactly this sum of momenta that we just wrote down here. So m1v1, m2v2, and so forth. So actually we can, there's a kind of a nice way to understand what the total momentum is. So we can either think of it just as the momentum of the total momentum of all the sub-particles, the constituent particles, or we could also just think of it like, okay, well, let's just think of this whole thing as one blob. And because we can rearrange this equation, right? So this thing here, we can and so this is the thing that we started off writing. Yeah. So the total momentum is, and this is just the total mass, right? So the total momentum, we can also view it in this way where it's, well, maybe we should write vectors on everything. The total momentum, we can also view it as the total mass times by the velocity of the center of mass, right? So we can view it kind of in two ways, where we can either view it as just the total momentum as being the sum of all these individual ones, or we just look at the center of mass of this thing, right? And then say it's moving this way. So we just look at the velocity of that center of mass, and we just add up all the masses here, and we can also calculate it in this way. So it can be, it could be calculated basically in two ways, one from a center of mass perspective, one from an individual particle perspective. Now you might wonder, and actually I wondered this, I mean, this is sort of a really basic and fundamental question, but a lot of these other things like forces are kind of relatively intuitive, right? So, acceleration and velocity, these are just sort of describing the motion of something, right? So, force kind of concept makes sense, we could push on something, right? And so that has but like this momentum concept is, I feel a little bit more abstract. That, why should we, have this quantity? Where does it fit in the whole sort of scheme of things? And, well, I would give sort of two reasons for saying why momentum is a good quantity to define. I mean, because you can conceivably sort of define all kinds of other funny quantities, right? So, but why define this particular quantity? Why do we say it's mv? Why is it not some other formula? Well, it has a kind of pretty natural definition once you already define things like, forces. So F equals ma, fine. You can sort of learn to live with that. And center of mass. Well, basically momentum is sort of the guy that's in between both of these ones, right? So if you just keep on taking time derivatives, so if you start with center of mass, and then you take a time derivative, then you end up with this momentum. Then you take another time derivative, then you end up with a force equation, right? So in a way, it kind of makes, it's kind of logical in that way. It if you define this guy, and you define this guy, then why not define this guy too? Because it's just in the sequence of time derivatives, right? So it has a kind of a natural mathematical definition. But it's also, of course, very useful in a practical sense. And basically the situation where it's useful is actually a little bit of a particular one because well, you need some kind of particular situation in order to define it, but it's useful in the case when you're looking at basically an isolated system. So if it so happens, and it doesn't have to be like this, if it so happens that the total force is 0, then this is 0, and of course because this is just time derivatives, right? So that basically means that this one will be constant, right? So just like a fixed number. And if it's a fixed number, what that actually means is that it will not change in time as long as the system is isolated, as long as f is equal to 0. So this is basically why, and we'll do conservation of momentum soon, but it's basically, momentum really is useful in this way because of this particular situation when there's no forces acting on the system, a lot like this this example here. So there's might be some internal forces acting on the system, but there's no external forces. And I guess you can usually find such situations, well, we'll look at those. But basically, it's useful in this way. Okay, so, but let's just do this to get our heads around it. So, figure gives the magnitude p of the linear momentum versus time for a particle moving along an axis. Force directed along the axis acts on the particle. Rank the 4 regions indicated according to the magnitude of the force, greatest first. Okay, so which one of these has the greatest force acting on it? And we don't have to worry about the sign, just the magnitude. So we want to relate momentum to force, right? So what formula do we have for that? Not quite. Well, yes. Multiplied by time, or
oh, sorry.
yes.
1, 3, 2, 4.
Okay. Let's finish your thought there. Yeah.
The force multiplied by time.
Yes. Yeah, that sounds better. Yeah. So force times time is equal to momentum. Time interval. Or force. Well, actually, this is also a change. So actually, the relation I was looking for was more like this. The time derivative of the momentum is actually equal to the force, right? Okay, so what was your answer? 1, 3, 4? Yes, 1, 3, 2, 4. So basically, this is gradient, right? So dp dt is just the slope, yeah? So the force is largest when the slope is the greatest. The gradient is largest. So this has got the largest gradient, it's the steepest. 3 is the same, well, it's going down, but it's got, if you're just looking at magnitude, it'll be the second steepest, I guess. 2 and 4, they're both the same, right? So they, actually the force on those ones would be 0 in this case. So yeah, 1, 3, 2, 4. Which region is the particle slowing? Yeah, 3. And then why 3?
Because the momentum is decreasing and momentum is equal to the mass.
Yeah. mv, yeah. So momentum is, it's just about velocity actually, right? You just multiply by mass and it's momentum, right? But so that's probably the simplest way to view it, but you could also view it from a force perspective. So this thing is traveling in the plus direction, and then the force is going to be here, it's going to be in the negative direction. So if it's going in the plus direction and the force going backwards, then of course it's going to slow down. Yes?
Because the P is negative in the formula on the whiteboard.
No. I think there's no minus on which one? This one here?
Yeah.
Right, yeah, so here the force will be negative, yes. Slope is negative. But then the P itself is positive, right? Well, I'm assuming this is 0 here. So P itself is positive, moving in the forward direction. Force, because the gradient is negative, will be in the negative direction. So if you're moving forward and the force pulling you back, then it will slow you down. Yeah. Okay. Now there's basically what this is talking about is just inverting this relation, right? So we know that momentum time derivative is the force. So okay, obviously we can go backwards and get the momentum by integrating the force with time, right? So I prefer to just call this momentum or change in momentum because I don't know, I don't want to remember another name, to be honest, right? But for some reason they call this one impulse. But to me it's just change in momentum. So change in momentum and impulse are the same thing. So here they define a new quantity, J, and say, okay, well, let's look at this quantity, integral of force with time. and then they say, oh, well, that's also equal to change in momentum. Okay, but to me it's like, well, I just inverted that one. So, of course I'm going to get, and this is a change in momentum because when you do this integral, you'll have some limits here, right? So you'll have the initial time and the final time. And basically this will give you the change actually in the momentum, not the momentum itself really, because basically you don't you don't know, like, say what the initial momentum might be. So just to give an example of that, so say you're hitting a ball with a baseball bat, right? Now if you took a slow motion camera and then looked at basically how much force was being applied to it, you'll find probably that actually, the force actually changes quite a lot with time, right? So just at the moment that it first touches it, it's just touching it. It's not really making any force on it. But then when the bat is in full swing of actually pushing this ball through, there'll be quite a large force acting on it. And then as the ball flies away, the force will again go down, right? So, well, firstly, what this relation is saying here is that the change in momentum of that ball will be equal to the integral of this force over time. And that's actually just the area under the graph of this relation, right? So the force, as it changes through time, you integrate the graph, and basically that's how much momentum is given to the ball, right? So if that's how much momentum is given to it. So it doesn't really tell you like what the ball's momentum was initially. Say, if it was standing still, then of course the final momentum would be equal to the area under the curve. But say the ball was already moving, then this would give this further momentum, right? So it depends upon how much it had at the beginning. That's why it's actually a change of momentum, not just a momentum. And sometimes, because this is a rather, funny shaped thing, just to get an idea of how much force is actually given to the ball, it's useful to sort of think of an equivalent amount of force that you might give it that gives the same amount of momentum. So suppose you change the shape of this curve such as to kind of flatten it and then make it into a box like this, right? So that the area underneath it was the same, so that it gives it the same amount of momentum. So basically the final result is the same. It's just that, how you actually applied the force is a little bit different. So essentially what you can do is, find, this would be what you might call an average force instead of this force that's actually changing over time. So whatever this integral was, so if you said, okay, so I know what that J is, and let's say the time interval is the same as whatever, time it took to hit the ball, then just by equating this to force average times delta T so that it's the same constant force throughout, I can basically find an average force instead. It's kind of like an equivalent force that gives basically the same result, right? So in real life it's like this, but it's a bit too complicated for our tiny minds. So just to give a slightly simpler version of it, but gives the same effect, you can instead quote an average force instead. And this is the way that you do it. Okay. Okay, I think we should leave it there. So I think we've got another lecture this Sunday, right? Some of you are looking surprised. Yeah, yes. Unfortunately, there's a lecture on Sunday. I think it's like a make-up day for one of the holidays. So, well, I'll see you here on Sunday next year.
The Sunday is make up for Tuesday and August.
Oh, I don't know. I mean, does it matter? Yeah. Oh, you mean for homework?
Yeah.
I see.
Wait, what? Homework is.
No, no. Let's just make the homework due on Tuesday.
Yeah.
Yeah. Okay. All right.